Some pizza. So welcome everybody to the start of the new Computational Science and Engineering seminar series. So under Professor Aluru's new CSE leadership, we're trying to start this seminar series again, and we're beginning with a sequence of talks, as you undoubtedly know, by faculty from Illinois who work in a number of diverse areas, all of which are heavily computational. So before I introduce today's speaker, I'll just point out that on the table back there, there's the list of upcoming talks. So please take a look at that. So we've got talks coming up, 2 talks in November and 1 in December, all by sort of active young faculty from this campus who are doing exciting things. And then the other thing that's on the table over there are these little bits of brightly colored paper where you can write suggestions for future speakers. So in particular, if there is somebody on this campus who's doing really exciting stuff that's computational that you would like to hear more about their work, then please fill this out, and you can either just leave it on the desk or give it to Jody or Professor Lura or myself, or email us and suggest people as well. Okay, so today's talk is first inaugural talk, I should say, is going to be by Elif Ertekin, who's an assistant professor in mechanical science and engineering, working in the area of material science, and she's going to tell us all about using computational methods to do first principles analysis of these challenging problems.
So thank you, Matt, and I'm very happy to be here, giving the first of what looks like will be a very fun seminar series. I will start off by talking a little bit about really trying to give some examples of what we can do with first principles computational material science. And my hope is that when this is done, you'll have an idea of both what we can do and also what we can't do with first principles modeling today. I thought I'd start with this quote that I thought was kind of interesting. It says, "One can describe the history of civilization as a series of breakthroughs in material science and chemistry. Beginning with the Stone Age, we have progressed through Bronze, Iron, Nuclear, and Silicon ages. Materials lend their name to ages because materials define technological capabilities. Advances in materials have shaped history and the balance of economic and military power. Iron and steel, gunpowder, ammonia synthesis, antibiotics, uranium and plutonium, silicon-based electronics." That was from a DOE workshop on computational material science about 2 years ago. And I thought that's a really interesting way to kind of think about the development of technologies and industries over the course of my highly nonlinear timeline here. And of course, the way that resolution works, I know more about this and have focused more on it. Perhaps if I had lived here, I would have had more to say about what was here. So there are today, if we look around us, what I would call a number of really interesting materials challenges. And really the question is how to design the material that you want to achieve the functionality that we're looking for. And this applies to a number of different types of systems, right? Solar cells. It's been 100 years since we made the first solar cell. They're still not optimally efficient. Automobile waste heat recovery systems. Wouldn't it be great if we could do something useful with that waste heat generated by your car? Thank you. Hydrogen-powered bus. I actually got to ride one of these when I was a graduate student at Berkeley. We had 2 hydrogen-powered buses kind of experimentally in our system. Lightweight, high-strength, high-temperature structural materials. Lightweight materials making our airplanes more fuel efficient. High-temperature materials allowing us to run our thermodynamic cycles more efficiently. Or similarly, high-temperature materials for turbine blades. This is an example of desalination turbine blade as well. The point I'm trying to make is that everywhere around us, we have a number of materials challenges. How do we design the best material for the particular application? And so the idea that I want to try to get across is that nowadays, there's a lot of inroads that can be made as far as discovery through simulation goes. we know that materials processes are critical elements for progress in energy systems, industrial technologies. And I would say that now we have at our disposal a very powerful collection, a collection of tools for synthesizing materials, processing them, characterizing them, and then a very good collection of tools for simulation and modeling of materials as well. And so today, really, we have what I would call a fairly unprecedented view of the atomic scale structure and dynamics of materials, thanks to these tools that we now have at our disposal. And really, for the first time, we're going to be able to synthesize, characterize, and model materials and chemical behavior at length scales where that behavior is actually controlled. And this is an exciting place to be, and it's why I'm excited to be doing the kind of work that I do. Is nowadays, when I say I want to put an atom here and an atom there, and I can look at my experimentalist colleagues and they don't, well, completely laugh at me anymore. They say, maybe we can do that. So the idea here is that integrated synthesis, characterization, and modeling of complex materials and chemical processes, in principle, could potentially transform our ability to understand and design new materials. Here's the caveat. The complexity of the material systems that we're putting together is also growing, right? And obtaining the type of performance that we're looking for requires optimizing many material parameters, many degrees of freedom, the particular chemistry of the material. Maybe you want a tailored micro or nanostructure or a designed electronic structure for the material. Here are some examples. So today's high-strength, high-temperature steels typically contain something like 6 to 8 different elemental components in a highly tailored or designed microstructure. This wasn't the case before. It used to be maybe 3 or 4 components. Here's another example. Today's integrated circuits. These are all of the elements that appear in modern integrated circuits nowadays. If you don't include trace elements in the human body, it's more than what appears in the human body. Or here, photocatalysis. Maybe I want to design molecules or surfaces that are tailored for catalyzing chemical reactions like water splitting. How do we do that? There's a lot of degrees of freedom in the chemistry of materials and surfaces and interfaces. And this is the kind of complexity that we are going to need to be able to model if we want to be able to address a lot of these challenges. And so I would say that we all know in the CSC seminar series that over the past decade, obviously, computational power has increased very quickly, advances in both hardware and software. And we know that this rate of improvement has enabled quite a bit of development of computer simulations, and I would say models of pretty unprecedented fidelity. And so from the computational material standpoint, I would say that nowadays, depending on how much accuracy we need to solve the problem at hand, we can now simulate the almost exact quantum behavior of several thousands of atoms and the approximate behavior of billions of atoms. Of course, capitalizing on all these opportunities, this materials by design dream, require a number of improvements to the state of the art in computational modeling and simulation. And so my goal is to discuss some examples of this today. And so with that kind of as an introduction, these are the topics for discussion for today. I realize that I gave a fairly ambitious abstract, so my talk is going to be a little bit narrower, but I hope to touch on everything at least a little bit. So I'm going to start just by introducing the idea of first principles modeling, Schrodinger equation. Then I'm going to give a couple of examples related to photocatalysis, so designing water splitting systems, and then a couple of examples related to high accuracy modeling of point defects in semiconductors. So just to sort of set the stage here, because this is a broad audience, I kind of wanted to introduce the problem that I'm mostly going to be focusing on for this talk. In quantum mechanics, the Schrodinger equation is kind of the analog to Newton's second law in classical mechanics. It's the equation we apply to atoms, to molecules, to solids, subatomic systems. And for example, for a single particle embedded in some sort of potential field, this is what the Schrodinger equation looks like. And if you haven't seen this before, you're thinking, what is that? Well, let me explain a little bit. First of all, the wave function is the function that we're interested in determining. It describes the quantum state of the system. It's the function that we actually want to solve for. If we know the wave function pertaining to a system of particles, we know almost everything we need to know about that system. And this Schrodinger equation that I've written here, it's a linear partial differential equation that describes how that quantum state described by the wave function evolves in time. Now, if you don't like this particular analogy, you'll have to blame Professor West, because it's in here for him, for his benefit. I said, what if I introduced the Schrodinger equation as being similar to Hamiltonian mechanics? We can look at this, and I want you to associate this side with the total energy operator, and this as being a Hamiltonian, a kinetic energy, and a potential energy term appearing here. Now maybe the equation still looks a little bit funny, and I would say if it does, you're having the right response to it. Don't take it from me, take it from a much smarter man. Richard Feynman once said about this, where did we get that equation from? Nowhere. It's not possible to derive it from anything you know. It came out of the mind of Schrodinger. Well, I can try to give a little bit more insight. If we think in terms of Einstein and de Broglie's insights into the quantization of light, these kind of critical ideas that said light is not just a wave, but it's also particles. That light can have both a wave and a particle-like nature, and these expressions here kind of make that connection, right? Here, these expressions connect in the blue, what I would call quantities we usually attribute to particles. Particles have well-defined energy and momentum, but they're now being connected to characteristics we usually associate with waves, angular frequencies, or wave numbers, right? So in the early 1900s, we kind of had this realization that we can describe systems as having a wave-like and a particle-like nature. And Schrodinger's great insight was he said, all right, I'm going to write down a wave function that looks like a plane wave. And he noticed a couple of interesting things about the spatial and the time derivatives of that plane wave function. In particular, that the Laplacian looks a lot like kinetic energy operator. And this time derivative here ends up looking a lot like the energy operator. And so, in some sense, you can kind of, if you're familiar or used to the idea of Hamiltonian mechanics, maybe that Schrodinger equation looks a little bit less unfamiliar. Here's a familiar example of the Schrodinger equation applied to probably one of the last problems you would actually analytically use it for in your quantum mechanics class, the hydrogen atom. We write down the Schrodinger equation here. Now I've written this down, it's in its time-independent form. So it's an eigenvalue problem here. And the solutions in this case exhibit a separable form, meaning that we can actually, usually from here, what we would do is write this down in spherical coordinates, and then we can actually separate that wave function into a radial and a set of angular components. Those are the eigenfunctions of this eigenvalue problem. The solutions for the wave functions. The eigenvalues are the energy of the system in that particular eigenstate. And so I put a label, of course, indicating that we label these wave functions. Typically, for the hydrogen atom, these wave functions are referred to as orbitals, right? And they're characterized by these quantum numbers. N is the first principal quantum number, L the azimuthal quantum number, and M is the magnetic quantum number. And if I were to take these guys and actually plot them, we would see what we're used to seeing. Hydrogen atom wave functions, s orbitals, p orbitals, d orbitals, other sorts of things. And so that's, I would say, a relatively straightforward example of the usefulness of the Schrodinger equation. But the problem is that it becomes much more complicated pretty much as soon as I have more than two particles in my system. So now instead of, let's say, a hydrogen atom, nucleus, and an electron, Let's say I have some sort of multi-electron atom, maybe a molecule, maybe a solid. So if I denote the positions of the nuclei of the atoms by these capital letters, the charge of the nuclei, capital Z's, their masses by capital M's, and then the positions of the electrons by these little r's, that Hamiltonian term in the Schrodinger equation gets really ugly really quickly. It becomes a many-body interacting problem. And so what the different terms that are appearing in here are, I've already simplified it a little bit actually. What I've done is I've fixed all the nuclei and said we're not going to let those move. As far as the time scale of electron motion is concerned, they're pretty fixed. And in this case, the different terms that are left at that point, this is the kinetic energy term associated with the electrons in the system. These two terms are the Coulomb interaction between the nuclei, capital R's, and between each of the nuclei, or between a nucleus and a particular electron. And then this is the interaction term between individual electrons in the system. And I'm going to break this up a little bit further. Because we're fixing our nuclei in space, we can think about this as being the external potential. This is the kinetic energy. And this part here is kind of the part that causes all the problems. This is the interaction term, right? The problem is the wave function itself depends on all of these coordinates of the electrons, and then it appears in the Hamiltonian as well. So you have to determine this wave function kind of self-consistently. So note here that the only part of this Hamiltonian that changes for a different system is this external potential here. So you can see how this problem becomes difficult to solve, and it becomes difficult pretty quickly. And historically, there are a number of different approaches that have been used to solving this problem. I've listed a couple of them here. Today, I'm going to focus on these last two, density functional theory and quantum Monte Carlo methods. And I'll explain a little bit what they are. Questions before I move on? Okay. All right. And I'll explain them through example in some sense. I will illustrate the application of density functional theory to photocatalysis. And before we start, here's one point I want to make. An underlying issue, a kind of a big problem we have, is that working with the actual wave function itself, the wave function is a beast of an entity. And here's what I mean by that. For example, let's consider the following possibility. Let's say we have n electrons populating a three-dimensional space. And we're going to divide that three-dimensional space into capital N by n by n, for example, 2 by 2 by 2 grid points. To reconstruct the wave function, which is a function of all the positions of all the electrons, how many points do we actually have to keep track of? So here's our space, and we are going to divide that up into a nice grid. Our wave function is a function of however many electrons we have in our system, and our grid is going to be divided into, in this case, a 2 by 2 by 2 grid. And from this chart, we can see that as the number of electrons increases, the number of points we need to actually keep track of the wave function grows immensely quickly here, right? The number of points that we're going to have to keep track of to be able to actually numerically represent that wave function becomes huge very quickly. But look at this. Let's say that instead of the wave function, I could work with the electron density, the total electron density. That electron density is a function of only 3 variables, right? X, Y, and Z, and however many grid points that you might have in here. And so no matter how many electrons we have, that electron density can be represented by the same number of points. And so this kind of motivates this idea that maybe the electron density itself seems to be a more manageable quantity than the wave function. And wouldn't it be nice if we could reformulate our problem, the Schrodinger equation, in terms of density rather than the wave function? Well, that's exactly what density functional theory is. It's a way of taking this many-body interacting problem that we have and mapping it onto an effective non-interacting problem. So in density functional theory, what we do is we take this interacting system of electrons and we map it onto an effective non-interacting system, where this electron has some sort of average or mean field interaction that describes the influence of all of the other electrons in the system. So this idea that you can take this interacting problem and map it onto a non-interacting problem, it turns out that that mapping does exist. It is, in principle, you could do it exactly. Got Walter Cohen the Nobel Prize in Chemistry in 1998. Some people are bitter because maybe he should have gotten it in physics. But anyway, he did get a Nobel Prize, so I guess you can't complain. A couple of notes on density functional theory. So first of all, you can show, and it's relatively easy to do, that in principle, for the ground state wave function, there is an exact mapping from this many-body interacting problem to some sort of effective mean field problem. We know it's out there. The trouble is, here's the rub, we don't know what that mapping is. We'll often refer to it as the exchange correlation functional, and we have to approximate it. We have to approximate it in reality. And so most conventional ways of approximating this mapping are based on properties of things like the homogeneous electron gas. And in my mind, because we take this mapping that we don't know and we approximate it with something that we can calculate, like that mapping for the case of a homogeneous electron gas, as a consequence of this, this means that when I model a system in DFT, it's going to be a little bit more like a homogeneous electron gas, a little bit more metallic than the material actually is in reality. And so if you think about it, a lot of our people who are familiar with DFT, we know that DFT underestimates band gaps. It's related to the fact that actually we're modeling the system to be a little bit more metallic than it actually is in reality. And so what we've done is we've traded these many-body interactions in our linear partial differential equation, the Schrodinger equation, and obtained in return an effective mean field, but now nonlinear differential equation. You get nothing for free in this world. All we know is that that exact mapping is probably entirely non-local in time and in space. But we may as well try. So let me show you a little bit about what we can actually do with a theory like density functional theory. I'm going to try to apply it to materials designed for photocatalysis. The idea here is to use computational modeling and simulation to design interfaces, integrated systems that are optimized for photocatalytic hydrogen production by water splitting. And this is work that I've gotten involved with through my involvement with the Eisner program here. And I work in collaboration with Lane Martin's group. They're an experimental group in the material science department. They're actually growing the systems that we're modeling on a computer, which is very exciting because what we model on a computer, they are able to layer by layer grow using pulsed laser deposition. So when it comes to designing systems for photocatalysis, where can computation actually play a role? Well, here's what we want. We want a surface. This is the 001 surface of titanium dioxide, which seems to be one of the better materials we have for water splitting. Seems to be reasonably okay at taking water molecules and splitting them to produce hydrogen as a fuel source. So where might computational modeling actually play a role here? Well, here's some thoughts. Identifying new materials systems for photocatalysis. Looking closely at the surface chemistry, identifying the active sites where water molecules might adsorb onto the surface, looking at reaction pathways on the surface, exploring charge transfer across interfaces between different materials. Here's how we decided to apply it for this particular system. What I'm showing here is a range of different semiconducting materials. And I'm plotting the valence and the conduction band edges for those different materials. And this gray box here gives us the potential that's necessary for electrons that are delivered to the surface of the material to actually participate in a reduction reaction that's necessary for water splitting. And then this lower edge shows you the energy level that's necessary for holes that are delivered to the surface of the material from the valence band edge to have in order to allow the oxidation reaction to take place. So we have oxidation and reduction necessary components of water splitting. And let me sort of point out how we look at this. Okay, TiO2 seems to be a pretty good material for water splitting. And what we can see if we look at the position of the valence and the conduction band edge here is that it has a very low valence band edge, which means that any hole that gets delivered to the surface, TiO2, is going to have a sufficient energy to drive the oxidation reaction. TiO2, on the other hand, doesn't have such a nicely positioned conduction band edge to deliver high energy electrons to the surface of the material. So for this particular material, on the other hand, what if we look at this material, cuprous oxide? Cuprous oxide, on the other hand, has a really good reduction potential, a high conduction band edge that can deliver electrons to the surface with enough energy for the reduction reaction to take place. Titanium dioxide, cuprous oxide. Here are our two materials that we're looking at. And now the question is, all right, what happens if we try to integrate these together, if we try to put them together? I'm not only doing this in a computational vacuum, actually. I'm doing this together with Lane Martin's group in the material science department, who's actually growing these materials, this heterointegrated system. And let me point, this is kind of one of the points where I'm going to point out one of the problems with density functional theory. And this is what it is. I'm listing here for these two materials the DFT predicted band gap in comparison to the experimental band gap. And you can see that that gap is actually pretty different. Cuprous oxide in particular is a pretty insidious case of the DFT band gap problem. DFT gap is half an EV in comparison to the 2.2 EV gap in reality. And so with a situation like that, how can we actually determine what the band alignment across this interface is going to be? How can we actually determine whether we have the desirable band alignment in this system to promote separation of electrons and holes that's going to actually give us the water splitting that we want? And really, I would say that the answer is that I don't have a good answer. I don't think there's a very good way to use DFT to predict band alignment in this particular scenario. Does that mean we can't use DFT to do anything useful? No. There are useful things that we can do, and let me show you what one of them is. Let me give you kind of a neat example here. This material, for those of you who maybe have been thinking about this a little bit, is actually, this interface is interesting for a number of reasons. One of them is that it's a polar interface. And what I mean by a polar interface is that if we look at this layers of material lined up one after the other, and if we model these two component systems in their ionic limit, what we see is that the TiO2 layers, zero charge, our ionic solid cuprous oxide has alternating charge on its planes. And if we were to integrate the Poisson equation for this charge distribution across this slab of material, what we would actually find would be that as soon as we hit that interface, our potential would start diverging. And that diverging potential in the thermodynamic limit that this becomes an interface between two bulk solids means that the energy of the system blows up, becomes infinite. This is what's called a polar catastrophe in the literature. And so if you looked at this and really thought about it, you would say, man, that system really shouldn't be able to exist in reality because of this polar catastrophe. It shouldn't be there. And this is where I kind of want to say, I think there's something neat we can do with this, which is that it's true that in the bulk thermodynamic limit, this material system is not stable. Something is going to happen. Maybe the interface will reconstruct. Something needs to take place to get rid of this divergence. But there's kind of this unique world where we can intersect finite size effects together with polar interfaces. In finite size or nanoscale systems, this divergence of potential doesn't actually occur. And so there may be this kind of neat playground in here where I can take a material that in its thermodynamic limit would be unstable, but through finite size effects, I could make it a little bit more stable. I could put it on the verge of an instability, or I could make it a really good water splitting system, potentially, because it's the material that is on the verge of an instability. And so that's the idea with this system here. So my student, Rajiv, has started modeling finite size effects in this integrated cuprous oxide TiO2 material system. So we're looking at putting individually, layer by layer, one layer at a time, of TiO2 on top of a cuprous oxide system and looking at how the surface chemistry of that system evolves. What's kind of neat about this is we can put this on a computer. Lane Martin's group in the material science department is able to layer by layer actually make this system as well. So we can directly compare his results to our results. Here are some of Rajiv's results actually illustrating that potential divergence. Let me just sort of show what's going on here. Y-axis is the potential. Z-axis is the position. Z-axis. This regime here is the cuprous oxide. And now he's showing what the potential looks like for different numbers of layers of TiO2 on the system. And you can see that as the number of layers of TiO2 increases, you can see that potential drop kicking in this system. What's kind of neat, we see it kicking in, but what we do see is that, at least at that particular size scale, those systems appear to be stable. And what's neat about that is that it matches up very nicely to Lane Martin's group's work. He's actually synthesizing these systems at the nanoscale. So he's able to grow using pulsed laser deposition small nanoparticles of Cu2O on top of strontium titanate substrates. He coats them with layers of titanium dioxide. And he's able to measure their photocatalytic activity. And so what we see is that at high thicknesses, where we think the instability kicks in, the surface reconstructs, we lose a lot of our enhanced photocatalytic activity. But in this regime where we can take advantage of these finite size effects or stabilizing factors, we actually see pretty enhanced photocatalytic activity. And so that is kind of one example of what we can do using a theory such as density functional theory. I actually had one more example related to photocatalysis. This is work that my student Chandini is working on, related to putting titanium dioxide now on top of a polarizable material. But just in the interest of time, I think what I'm going to do is let you know that we're also working on this. This is, the idea here is to now integrate titanium dioxide with a perovskite that can be polarized. The idea being that if we now switch the underlying polarization of the perovskite material, we can change the surface chemistry of the TiO2 layer on top and thereby try to tune it for photocatalytic reactivity. And Chandini's made actually a lot of progress on this, and I'm sorry that I'm not going to be able to go into a whole lot of detail. I will just sort of summarize her great insight that we had, which is that in these sandwich structures, what it takes to bring about a good, strong polarization is symmetry breaking, right? Is taking our sandwich layer here, this is our polarizable perovskite material. If I just put TiO2 on both sides of it and allow the system to optimize itself in DFT, what I see is the system loses its polarization completely. If I somehow break the symmetry of these boundary conditions by introducing defects at one interface and not at the other, we see that our polarization comes back. And in fact, for the right combination of point defect in engineering at the interface, we can actually get higher polarization than what we had in the bulk system itself. I do want to spend a little bit of time talking about high accuracy modeling of defects in semiconductors using quantum Monte Carlo methods, because this is something I'm really excited about, and this is something that I think once we get Blue Waters up and running here, I will be very, very happy to take advantage of and be able to use many of the computing cycles on to be able to apply quantum Monte Carlo methods to quantitatively describing the properties of point defects in semiconducting materials. So let me just set this up a little bit. Really accurate quantitative prediction of point defect properties, things like thermal or optical ionization energies, would be a very useful thing for point defect engineering of semiconductors. But I would say that quantitatively modeling defects has proven to be pretty challenging using first principles methods. For example, that band gap problem that I talked about in DFT really comes back and kind of rears its head when it comes to trying to determine what a defect in a semiconductor is going to do. Here's a pretty classic example. If you think about a nitrogen impurity inside of a zinc oxide crystal. If we look at our periodic table, most of our semiconductors come from this row here, group 4. We have some semiconductors that are 3 5s, and then we have our 2 6s. Zinc oxide is a 2 6 semiconductor. Now, if you think about it, if I were to remove an oxygen atom and replace it with a nitrogen atom, well, I'm just taking out an oxygen atom and replacing it with something that's actually pretty similar, right? Just one column over in the periodic table in the same row. It's missing one electron relative to that oxygen atom. So you would think, okay, this should be a good defect for introducing p-type conductivity into zinc oxide. Seems to make sense. The thing is, nobody's really been able to obtain p-type conductivity in zinc oxide. There are a couple of reports in the literature of p-type zinc oxide, but by and large, it seems like an experiment. It's not reproducible. Now, let me talk about modeling of that particular defect. Zinc oxide is another kind of insidious case of the DFT band gap problem. If you think about it, here's the band structure of zinc oxide. Here's the gap in DFT. It's about 0.9 eV. That's in comparison to the experimental band gap of 3.2 eV. And so let me highlight kind of what the problem is. Here's our experimental band gap in zinc oxide. That nitrogen impurity is going to put a level somewhere in here. We don't know where, but that's what we're interested in determining. Well, in DFT, if my gap looks like this and I don't even know where it is relative to here, how am I going to be able to figure out where that nitrogen defect level is? So the band gap problem really does cause more dramatic consequences in problems like looking at defect energy levels and band gaps or other sorts of things. And so what I became kind of interested in doing was making use of high accuracy methods based on quantum Monte Carlo to calculating point defect properties. Quantum Monte Carlo motivate it kind of in the following way. I'm summarizing here a lot of techniques that are most commonly used in trying to describe the properties of point defects in semiconductors. DFT, I'm giving the computational scaling for the method here. Whether it's directly based on the Schrodinger equation or not, whether we can expect an accurate band gap or not, or an accurate total energy or not. And what I want to point out about quantum Monte Carlo is that it is the only one that is directly based on the Schrodinger equation. Being directly based on the Schrodinger equation is a great thing. All of these other models use some kind of intermediary model or other approach, which means that we're not guaranteed that if we do a better job of solving those equations that we're going to get the right answer. When we directly worry about the Schrodinger equation, we know that if we do a better job of solving the equation, we're going to get the right answer. So consequently, yes, we can expect to get accurate band gaps and accurate total energies. And the scaling is actually pretty good, right? Compared to DFT, it's got an n-cubed scaling as well. That's great. It's got a prefactor of 100, but really, of the two numbers that could be different, the prefactor or the exponent, I would take the prefactor to be different. That just means I need a 100 times bigger computer. So QMC, kind of in comparison to DFT, this is how I think about the two techniques. We talked about DFT already, and we talked about how what we do is we take this Schrodinger equation and we map an interacting problem onto a non-interacting problem. And I would call that the workhorse technique of the computational material science community. But what about QMC? Well, what we do in quantum Monte Carlo methods is we actually we kind of bite the bullet. We deal with the real many-body interacting Schrodinger equation. And it's a statistical approach to solving the interacting many-body problem. We do it in a number of different ways. Variational Monte Carlo is one. Diffusion Monte Carlo is another. Diffusion Monte Carlo, if you look and stare hard at that Schrodinger equation, it kind of looks like a diffusion equation, right? There's a time derivative on one side and a second order spatial derivative on the other side. What we do in diffusion Monte Carlo is we make some kind of starting guess at what the distribution might look like. And then we use those diffusion sort of rules to evolve that distribution in time and kind of converge to the ground state. And so if DFT is the workhorse technique, I would call QMC the bulldozer. But wait, the bulldozer. It's big, it gets the job done, takes a little bit more computational effort, but we know we're solving the right problem. This, by the way, I'm really excited about applying QMC on blue waters because I think it'll be really great at looking at some of these point defect problems. So here's one example of looking at an application of quantum Monte Carlo methods to quantitative descriptions of point defects in solids. There are a couple of, in the point defect community, there are a couple of properties that we're generally interested in computing. The first one is the formation energy of the defect. How much energy does it cost to put the defect there in the first place? And we can write that in what looks kind of like a complicated equation, but really all this is a particle balancing equation where I'm saying the formation energy of a defect is equal to the difference in energy between the system with the defect versus the perfect system, plus a couple of terms here accounting for the fact that I may have removed atoms from or added atoms to a reservoir, or electrons to or from a reservoir as well. So this is effectively a particle balancing equation here. Defect formation energy, that's one thing we're interested in. Other things that we're interested in are thermal ionization energies. These thermal ionization energies are important because they tell us how effective a particular defect is going to be at doping in the semiconductor. Namely, if I plot the defect formation energy for a particular defect, but at different charge states, these points where the favored charge state of the defect changes is the thermal ionization energy. And whether that appears deep inside the band gap or near the band gap edges tells us whether it's going to be an effective dopant for the material. Optical ionization energies. Here's something else that we're interested in actually calculating. An optical ionization energy, what this means is, let's say I take my semiconductor with defects in it and I shine light on it. Because that defect is there, maybe that defect is able to resonate with certain wavelengths of light that are coming in. I'll be able to take that defect will absorb a photon of light, be excited from some sort of ground state configuration into some sort of excited state configuration. And that energy that it absorbs, associated with that photon of light, that's an optical ionization energy. Defects can also emit photons, going from an excited state to a less excited state. That's an emission that might take place. So what we were able to do, which was really exciting, was use quantum Monte Carlo methods to predict the thermal and optical ionization energies for this material, magnesium oxide. To my knowledge, it's the first time that QMC has been used in the prediction of thermal and optical ionization energies for a material. You're looking at this and thinking, that's not a semiconductor, that's an ionic solid. You're right, it is. This thing has a, as you can see, it's clear. It has a large band gap of about 7 or 8 eV. I'll also talk a little bit, go back to the zinc oxide problem where we've also applied QMC methods. Here's what our magnesium oxide crystal actually looks like. Magnesium oxide, rock salt structure, magnesium and oxygen atoms. And here's the band structure of this material according to DFT. DFT band gap 4.8 electron volts, experimental gap 7.8 electron volts or so. And so this is kind of a good place to point out some of the issues with band gap problems when it comes to looking at properties of point defects in semiconductors. In reality, this gap should be around 7.8 electron volts. In DFT, it's closer to 4.8 electron volts. DFT puts a defect level in the gap somewhere, but I don't have a good idea of whether it's right or not because it's not getting the band gap right in the first place. Here are the charge distributions associated with the ground state of the defect and the first excited state of the defect. And so what we've done for this particular system is we actually had to use a little bit of DFT and a little bit of quantum Monte Carlo. We used DFT to predict the local relaxations that take place around this missing oxygen atom, right? That's the defect that I'm looking at, is a missing oxygen atom. It's called an F-center defect, a Farb center, in different charge states. I use DFT to predict the relaxed structure of the atoms around that defect. Can't do that in QMC, not yet. And I decide to trust, for now, those DFT predicted configurations. And then using these DFT generated configurations and states as a starting guess, I use those now in my QMC analysis to compute the energies of these different systems here. Put those into quantum Monte Carlo. And by doing that, by actually computing the formation energies, I can compute and compare defect formation energies here in DFT for the neutral defect, the +1 ionized defect, or the +2 ionized defect. You can see where those thermal transition levels kick in according to DFT. But here's what I want to point out. This x-axis domain here is going from 0 to about 4.8, the band gap of magnesium oxide according to DFT. That's where we know the problem is. In this particular case, this band gap is off by almost a factor of 2. So let me talk to you a little bit about what I did for this system in quantum Monte Carlo. Before I do that, I want to make a shameless plug. This is the quantum Monte Carlo code that I'm using, QWalk. Lucas Wagner is here, he's the main developer of the code. Open source package, scales beautifully up to more than 20,000 cores. Lucas thinks it scales more than that. He just hasn't been able to get more than that. And I feel like I have to make this plug because I'm kind of the annoying person who finds the bugs in the code and go to him and say, I think there's a bug in the code. So I'm very grateful, of course, that he's able to work with me quite a bit on making this code work so that I can apply it to some of these large-scale calculations that I've been working on. So let's say we take those DFT configurations and we try to now apply QMC to the same system, magnesium oxide. The first thing I want to show is that, first of all, quantum Monte Carlo, unlike DFT, does a really good job of getting the band gap right for the system. Now in quantum Monte Carlo, this is an expensive proposition because it's not a single calculation like it would be in DFT. We have to do an extrapolation to infinite size system. But if I calculate an optical excitation energy for a 16 atom, 32 atom, 64, and 128 atom supercell, extrapolate this back, I get an optical gap of 7.96 plus or minus 0.06 electron volts. And that compares really nicely to the experimental value of the band gap. Optical excitation. I can also calculate using QMC the quasi-particle band gap. So here, instead of exciting a carrier from the valence band up to the conduction band, I can either add or remove a carrier and compute the quasi-particle band gap. And that also gives me a consistent result. That number is 7.89 plus or minus about 0.1 eV according to QMC. So you can already see that we're doing a much better job on the band gap than we were in DFT-based calculation. So onto the defect calculation itself. We know we're describing the solid material well. For the defects, I stick with those DFT relaxed geometries. I freeze them in. And then I use those DFT to obtain the orbitals, and I use those as my starting guess for the QMC trial wave function. And I compute those defect formation energies then using the standard equation for the approach for these energies. And here, now is a comparison of the DFT predicted and QMC predicted defect formation energy for the neutral and the positively charged oxygen vacancies in magnesium oxide. The biggest difference here really is the range of band gap. DFT, I'm limited from 0 to about 5 eV. Quantum Monte Carlo, because we're doing a good job on the band gap, gives us a much more realistic description of the system. This is an interesting system because here, you might say qualitatively, it really hasn't changed the picture too much. Those transition levels occurred somewhere mid-gap, and they are also in Quantum Monte Carlo. That's true for this system. I think it's because this is a pretty ionic system, magnesium oxide. We found this to be the case for MgO, where I think even the DFT description, it remains fairly ionic. For a material like zinc oxide, we actually found a very different situation, which I'll show you as well. So the last thing that I do want to show, as far as magnesium oxide goes, is a comparison. This is actually really exciting to us, of these optical transition energies. And this says when I have a defect present, is that defect going to absorb light of particular wavelengths or emit light associated with transitions in the charge states for that defect? And what's great here is those QMC numbers compare really nicely to the experimental numbers for the most part. They actually compare really nicely to recently published high accuracy GW results. They compare very well for absorption, not so well, I would say, for emission to experiment, but they actually compare really nicely to GW computed emission values. And actually this led us to think that this is an interesting situation where two different high accuracy techniques are getting similar results that are different from the experimental values as far as the emission is concerned. And this led us to think that, well, maybe it's worth going back and doing some spectroscopy on this system again and looking at these experimentally computed numbers one more time. If two independent high accuracy approaches are agreeing with each other so well, it might invite re-investigation of the experimental numbers. So that was our test case, actually, and I've run out of time, so I'm going to just cut to the chase. Zinc oxide was by far the more interesting QMC problem, and let me show you the punchline. Zinc oxide, here's the punchline. This material is one where Quantum Monte Carlo actually changes the nature of the defect level. In DFT, nitrogen looks like a shallow defect. If we put it into Quantum Monte Carlo, it becomes deep. And that is in better agreement with most of the experimental results that are now actually out there. So, you know, for the case of the defects in magnesium oxide, DFT and QMC gave qualitatively a similar picture. I would say zinc oxide is a little bit more of a problematic case for DFT. The band gap problem is pretty severe. Those d electrons that appear in the zinc atom cause DFT to give the system a pretty poor description. QMC is able to do a good job, however, and so we were encouraged to see that our defect transition level occurring around 1.5 eV above the valence band edge actually is in pretty good agreement with hybrid DFT calculations and GW calculations for the same system. Couple caveats: we're stuck modeling small supercells in this system. It is still a very expensive calculation. Okay, so with that, I've overstayed my welcome. So I'm going to stop here and just end by saying I think it is a really exciting time for computational material science. There are a number of quantities we can compute from first principles now. And we can almost directly compare our results to experiments. So this puts us at a really interesting point in time where the models can be improved by the experiment, and the experiments can get a lot of insight from the modeling as well. And that's what makes it kind of fun to be doing what it is I'm doing here. So thank you very much. I'll just stop there.